Hello, everybody. How are you doing? Hopefully everything's going well for you. Everything's good for me and my son, Gavin. We are going to start chapter 10, which is over gases. I have good news for you. This is the last chapter that we'll get to, and we won't even get to a test, so you won't have the test on this. So you guys have just a little bit of class left. Seniors, even less of class. Okay, chapter 10 is on gases, and you should have written your terms and your Bible verse for chapter 10 and turn that in. Your Bible verse is Matthew 24:12, and it's actually not very long. It's, and because iniquity shall abound, the love of many shall wax cold. Later on in this lesson, I'll tell you why I picked this Bible verse. It does apply to gases. Okay, you'll have your notes that you can find in the activities for chapter 10 notes. So when you're in your lesson plan, you will be able to find your notes, and you can download those and print them. So you can write on them by hand, or you could type them in on the screen in a Word document and save them that way. But there are a little bit of math problems in this that we'll get to, and so you want to make sure you know how to do those and that you write those down for yourself. Okay, Roman number 1 is the nature of gases. And letter A, it says kinetic description of gases. If you remember what kinetic means, anybody? It's talking about movement, okay? And so movement is talking about how do gases move? What is their movement like? Okay, the first one, gases consist of a large number of independent particles. So when we look at gases, they have a lot of particles because they're so teeny tiny. But yet, because their size is so teeny tiny, there's huge space in between them. And so that's why with gases, like if we take a balloon and we blow it up, and we can actually compress the balloon a little bit without it, if it doesn't pop. But because gases have a lot of space in between them, so we can push those molecules closer together. And so there's a lot of space, air in between, where we can actually compress them because they are small and very far apart. Number 2, the particles move at random, so no set direction, with high velocities, very fast moving, 1,500 to 4,000 meters per second, or 3,000 to 9,000 miles per hour. So that is incredibly fast. If we could actually see all the gases around us, the oxygen, the nitrogen, the argon, anything else that's in there, carbon dioxide, we probably would be having serious trouble concentrating, because if we could see all the gases that are actually just bouncing everywhere, beating upside us and the desk and the computer, just everywhere. Gases are everywhere, flowing and moving high rate. So they collide with each other, and then they move to another direction and collide with other gases constantly. So very fast, high rate velocity. Number 3, particles are separated by great distances. So I did describe this a little bit in 1, compared to the size of the particle. So there's billions of gases around us, but because they are so tiny in their size, they are very, very far apart. And strong forces stifle the motion. So if something were, like a gas is to collide into something, it stifles the motion as far as its direction, but it doesn't slow it down or change it because it's high rate of speed. Number 4, particles only interact during momentary collisions. Any other forces like gravity, electrical energy, chemical energy, they're all neglected. So gases are so light and they are moving so fast that they collide with each other. But again, with such space in between, they have to move a long way in order to collide with something as far as the another gas particle. Anything like gravity, electrical, chemical energy, it just has no impact on gases because they are so lightweight and small. They're not impacted by these energies. Many collisions occur every second. Air molecules may collide 5 billion times a second. So again, imagine if we could see all the gases around us just all over the place. 5 billion times a second. I think we all would have a serious case of ADD, hard to pay attention. Number 6, collisions are elastic. So think of a rubber band. If I stretch a rubber band out and I release it, it's going to snap back to its original position. After two particles impact of gases, the sum of their energies is unchanged. So I may have one gas particle moving really fast and the other one's moving fast too, but not as fast as the first one. But the first one strikes the second one. And so it'll cause the second one to slow down just a little, the first one to slow down a little bit, but the second will gain the energy. So no energy is being lost. So they will change energies higher or lower in between their collisions, but overall the energy is not changed. And number 1, we've got low density. Compared to solids and liquids, gases have hardly any mass per volume. And so we've talked about solids and liquids. Now we're talking about gases. They are so light, and that's why often they're floating up in the air. As an example comparison, we've got ice. It's 0.92 grams per milliliter as far as its density. And compare that to water, 0.997 grams per milliliter. So a density. And then we've got steam, which is very, very, very small density compared to ice and water. So big difference. We've got physical properties continued. Number 2, diffusibility. Gases spread out to fill the total volume evenly. And so an example of this, say if your mom is baking a delicious chocolate cake in your kitchen and you're in your room, and eventually you're going to smell that cake. And so that is diffusibility, so that those particles will continue to collide and spread out until they fill the room or rooms of your house evenly. And that's diffusibility, able to spread out and fill the total volume evenly. Same thing, we spray on perfume, eventually someone else is going to smell it. Number 3, permeability. Gases move into the space between other molecules. So they're able to go through other things. Gases, we can have them go through our clothing. Some people have athletic clothing that allows it to breathe, talks about being breathable. And that is talking about the gases being able to flow in and out, oxygen and all the air around you. An example of this also is permeability is your eye contacts. If you wear those, they are gas permeable. They allow gas, specifically oxygen, to pass through your contact to get to your eyeball. If you do not have this happen properly, you're going to have an issue with your contacts. I have a true story about this that happened to me years ago in the 90s when I first got my first pair of contacts, eye contacts. They were called extended wear, and they told us we could wear them up